Hello, how's everybody doing? Hope we're having a great day. Got a little video here on our next unit or our next lesson in Unit 4. It's really just a continuation of what we learned in the last unit, or heck, the last lesson, with definite integrals. Okay, so we've learned what this notation right here means. All right, we know that means we got some function. All right, we're taking the area under the curve between 1 and 3 specifically for this problem. Okay? So that's called a definite integral, and we know how to do the formula for that. Okay? So I got a warm up here for you to try it. It's already completed right here. It's completed on my notes, but I encourage you to pause the video and maybe try this on your own. And if we have time, which this is a longer problem, we probably won't have time to do it in class. But again, it's a good problem. I encourage you to do it. But pause the video, see if you can get this answer. Okay. And the only reason it's long is because it is a cubic function. Cubic function means we're going to have a little bit more terms, so it looks like a lot, but it's still the same steps. Okay. All right, let's jump into into today's lesson. So I went over this yesterday's notes, but we're using these today, so I think it's helpful for us to again just kind of have on record what they are. Okay, so here are some properties of. So these properties are of integrals here. Okay, so this first one is if we have the area from A to A, it's always going to equal 0. Because if you think about any graph, if my interval is just going from A to A, there is no length there, there is no rectangles, it's literally just, like, there's no dimensions, so that would be equal to 0 for an area. Again, number 2 is going to be more like context oriented later on down the road, but basically this is talking about direction. Okay, so like if we're taking the area underneath the curve from A to B, is if we're going from the lower bound to the upper bound, okay, that's going to be a positive area. Going from the left to the right is going to be a positive area. Now, going backwards, B to A, okay, backwards means that we're going to be taking a negative area. Going backwards when computing area makes it negative, okay? So negative times a negative would make a positive, which would make that equivalent. So that's what that's saying. So again, going backwards makes us take a negative area. If I want to make us go forwards, make us have the lower bound on bottom, we just put a negative out front. Okay, we'll see examples of that later. I think number 3 makes a lot of sense. It says if we're going from A to C, but we break it up between B, those areas are equivalent. So what that's saying is if you have this graph right here, here's A, here's C, and here's some B value in between it, like it's saying. All this expression means is that the area from A to B plus the area from B to C is going to equal the area from A to C. I think logically that should make sense. We talked about number 4 yesterday too, and I like number 4. It says if you're taking the area underneath the curve of a constant, it's just K times B minus A. And what we mentioned yesterday is that K is the same thing as saying like our height, and then B minus A is like the same thing as saying like multiplied by our length or our base. Let me give you an example. What if I said the integration from like 1 to 3 of 5 dx? 1 to 3 of 5 dx. Well, let's think about this. This is saying to find the area underneath the curve, 1, 2, 3, 4, 5, of 5 between 1 and 3. So think about what shape this makes. This is nothing more than a rectangle, right? And how do you find the area of a rectangle? It's just length times width, or base times height. The height, or our K value, is 5. And the base between 1 and 3, B minus A, is just 2. That area would be equal to 10. So taking the area of a constant, again, is just doing a rectangle. 5 and 6 are very common properties of a lot of things that we do, right? If you're taking the integral of 2 functions, adding or subtracting together, we can split up the integration. Okay, so just like we can with summation and limits and stuff like that. And same thing for this next part. If we have a constant being multiplied by a function in the integral, the constant can come out. Okay. So there you have that, some properties. I didn't mention these. I went over, or I showed these properties yesterday, but these are comparison properties of integrals, comparing two functions together. And the notation may seem scary at first, but if you draw it out, I mean, it should make sense. It says if you have a function that's greater than 0 for all of x between a and b, then the area underneath the curve is going to be greater than or equal to 0. Doesn't that make sense? Here's a to b, here's a, here's b. It's greater than or equal to 0 for every single x value, so it's always above the x-axis. And we're going from a to b. So wouldn't this area always be positive? I would say so. What about the next one? If we have a function f that's always greater than or equal to g for every single x on a to b, then wouldn't the area for f be greater than or equal to the area for g on the same interval? Let me draw that out real fast. I'll draw it right here. So let's say that we have, okay, here's a, here's b. So anyway, so like let's say like this right here is our function f of x between a and b, and this is my function g of x between a and b, right? If I take the area of f of x, which is the area underneath the curve of f of x, wouldn't that area be greater than the area underneath the curve of g of x? I think so, right? That's what that's saying. So I think that's a pretty logical statement. All right, now this last one sounds weird, but what it's saying is if you have some m, lowercase and capital case, which are just constants. So if you have these two constants that are between, on either side of f of x, okay, for all of x, then m times b minus a and capital M times b minus a is going to be on either side of the area underneath the curve of f of x. Now, we know from a previous property what m times b minus a and m times b minus a. We know what that means, okay? Like here's lowercase m. Here is capital case M. And so like we're looking between like A and B, right? Well, and then here is f of x that was said to be in between them. So it looks something like this, right? Well, we know that this is the area underneath the curve of M, and this is the area underneath the curve of capital M. So we know, so what it's saying is that like if you took the area underneath capital M, and you took the area underneath lowercase m, then the area under f of x is in between those two areas. Can't you logically see that right now? So there you go. Okay. Just three comparison properties, just kind of interesting things. Now let's put all this stuff to practice. Okay, so these are just, I see these questions pop up a lot with multiple choice as well, so it's good to go over. And they're just practicing understanding the properties and the definitions of a definite integral. Okay, so for instance, like look, like we're doing the area underneath the curve from 2 to 8 of f of x dx equals 15. And from 2 to 4 of the same function is 7. And it wants to know about 4 to 8. Okay, well, think about how that can set up. 2 to 8 is a big area. Then you kind of got it broken up at 4. You see that? So look, the integration from 2 to 4 of f of x dx plus the integration from 4 to 8 of f of x dx, isn't that going to equal the integration from 2 to 8 of f of x dx, right? It's like that example, you know, this is like a to b, b to c, well, that's the same thing as a to c. We kind of drew that earlier, right? So this is just as simple as saying, like this whole thing's 15, this equals, I know that 2 to 4 is 7, so 7 plus what gives me 15? Well, it's just 8. Okay, simple as that. Good exploration. All right, look at this one. It says, okay, we're going from -5 to 0 of g of x is equal to 12 then what is 0 to negative 5 of g of x plus 8? Okay. Well, okay, look. So here is from like negative 5 to 0, right? Of g of x. Negative 5 to 0 going this way, going in the positive direction. That's equal to 12. Well, going backwards is the same area. So we're going from 0 to negative 5, but it's negative. So this right here is the same thing as negative 12 plus 8, which is equal to negative 4. So that's what that means. Okay? That's a directional thing. So originally negative 5 to 0 is 12, but going backwards would be negative 12. Lastly, what about this one? Okay, 1 to 6 is pi plus 3. And then the area underneath the curve from 1 to negative 3 is equal to 8. I want to know what's happening from negative 3 to 6. So negative 3 to 6 is kind of the full thing there. So let's kind of see what's going on here. All right, look, 1 to 6. Okay, so 1 to 6. So this is, okay, if we're going negative 3 to 6, let's write out the full thing then. Negative 3 to 6 of f of x dx is going to be equal to. It should be equal to the integration from negative 3 to 1 of f of x dx plus the integration from 1 to 6 of f of x dx. So it's the same as that property, you know, a to b, b to c, then a to c. Okay? So I'm looking for this right here. Okay? Well, I know that 1 to 6 is pi plus 3, right? Okay. Well, I know that 1 to negative 3, so like the upper bound to the lower bound going backwards is 8. So that means that the reverse of that would be negative. So this will be negative 8 plus pi over 3. So my final answer would just be pi minus 5. Okay. So utilizing some of our properties there. Okay, now I got a couple more examples, and I like these because they're dealing with graphs, and it's fun to, or I think it's nice to look at these graphically. Okay. All right. Let's do this one. It says f of x is a piecewise function consisting of two line segments in a semicircle, which you see right here. Determine the values of the following. Okay, so this is just, again, understanding what this is asking. From negative 2 to 2. Okay, so here is negative 2, and here is positive 2. It wants me to find the area underneath the curve of that. That's nothing too terrible. That's just area of a semicircle with a radius of 2, which is 1/2 pi r squared, or 2 pi. So the area underneath the curve from negative 2 to 2 is 2 pi. What about from negative 5 to 0? So I'll do that in red. Negative 5 to 0, so here's negative 5, and here is 0. So that's asking for this area here and this area here. Okay. Well, okay, so this area right here, we're going left to right, so but it's a negative area, right? It's negative because we're underneath the x-axis. So going left to right, underneath the x-axis, that's negative. And it's a triangle, so that's base, which is 3, times height, which is 3, divided by 2. So this is negative 9/2 for the area of the triangle. Okay. And we already know that the semicircle is 2 pi, so half of that semicircle would just be pi. So my answer is negative 9/2 plus pi. Okay. All right. What about this next one? This next one's pretty cool. It says, what about 4 to negative 2? Okay, so here is 4, here is negative 2. Now it's wanting me to go backwards. Okay, so just know whenever it's going backwards, it means to like change the sign or negate your area. Another way I like to write this, so I never mess that up, is I like to flip it so I can always go forward. So I like to say negative area from negative 2 to 4. of f of x dx. I think if you flip it and always make the lower bound on the bottom, I think, and then just change the sign, I think that will really help simplify some of these problems. Okay. So the semicircle, so it's wanting me to do the semicircle, which I already know from number 1 is 2 pi. And this triangle is base times height divided by 2. So that's 2 times mother. Why are you doing this to me? Okay. So we're going over 2 up 1, 2, 3, 4. So 2 times 4 is 8. 8 divided by 2 is 4. So this is 4. Okay. So we got 4. And we got 2 pi. So the area would be 2 pi plus 4. But it's negative. So negative 2 pi plus 4. And you can leave it that way. You can distribute the negative, but there you go. Okay. All right, and then lastly, we got negative 2 to 5, which again, because the lower bound is on top, I think if you switch it, it makes your life a little bit easier when computing. Okay, oh yeah, and there's negative, apologize. Okay, so we're doing negative 5 to negative 2, negative 5 to negative 2, which I already know what this area was from a previous problem. That was negative 9 halves. So this is equal to negative 9 halves, which is positive 9 halves. So it was the same question or the same answer as before, but because we're going backwards, it makes that negative area now positive. So a negative kind of cancels each other out, which is a pretty interesting concept. Okay. All right, and then I'm going to do one more problem. So there's 2 more problems on the notes, but I just want to do one more in the notes. I want to save this one for us together because this is a 2005 AP free response. It's a number 5 question from it, so I think that'll be a good one to come back to. For now, we're just going to do this problem. Okay. So the graph is given. It looks like 3 or 4 lines there. Determine the following. All right. Negative 4 to 4 of this. So that's the area underneath the curve from negative 4 all the way to 4. That's the entire dang thing. You do it however you want. I have some students, like some students will see this as an entire trapezoid. Take the area of the trapezoid if you really want to, which is 1/2 our height, base 1 plus base 2, if you want to remember the area of a trapezoid. But if not, I think from a conversation last year with my students, even if they remembered that, they like to divide it up as a triangle, a rectangle, and another triangle, which if that's how you like to do it, it's okay. So that would be over 2 up 2. So divided by 2. This triangle is actually just 1, I believe. Over 2 up 2 divided by 1. This rectangle right here is over 1 up 2, so that's going to be 2. Oh wait, I think I messed up the area before. This is 2 by 2. 2 times 2 is 4 divided by 2. That should be 2. I'm sorry. So that triangle is 2. That rectangle is 2. I believe this one is the one that is 1. Okay, so 2, 2, and 1. And then we got to figure out the area of this mess here. Now just remember, since we're going left to right here, this area is going to be negative. Okay, so let's maybe break this up. How about, let's do like a triangle maybe, square. Maybe we can divide it up like that. Like this area would be 2 by 1, 2, 3. This is a 2 by 4. So 2 by 4 is 8 divided by 2. This will be negative 4, I believe. Check my math on that. This is 2 by 2, which is negative 4. And this is a 2 by 2 triangle, which is negative 2. Okay. So adding all that together, like the positive area was 5, and the negative area was negative 10. So my final answer is negative 5. There's more of a negative area than a positive area, so that's why my final answer was negative. All right, what about 0 to 4? Again, I like to change that to negative and say 0 to 4. Just make sure I keep everything consistent. Okay, so I'm going from 0 to 4. So here's 0. Okay, here is 4. which I already know from the last problem that this whole area was -10. So this is going to be -10, which is +10. So the reason is because it's a negative area underneath the curve, but because I'm going backwards, the negatives cancel each other almost. So it's +10. All right, what about this next one? This next one's -2 to 1. It's already, low bound to upper bound, so I don't need to worry about flipping anything to make sure my signs match up. Here's -2, here's +1. Okay, so we already said earlier that this was 2, this was 1, and this is a 2 by 1, so this should be -1 right here. So if we add all that stuff up together, it's like actually like this positive area, this negative area cancel out. Oh my goodness. And I'm left with an area of 2. All right, let's try this last one. This last one, area underneath the curve from 2 to -3. 2 to -3. Again, since the lower bound is on top, let's go ahead and change this to, come on now. Let's change this to -3 on bottom with 2 on top, and we're going to just make it negative. Okay, so -3, which is right here, all the way to 2, which is right here. Let's find that area. They just love to make this complicated for us, don't they? All right, how about we break it up this way? So like, okay, so I know this was 2, this was 1. I know that this is 1 and this is a half. Okay. And I know that this entire triangle is a 2 by 4, so this ends up being -4. Okay. So we're going to add all that stuff up, and because it's really going -3 or 2 to -3, it's going to change the sign. So we'll add it all up and then we'll negate it. So we got 1 and 1 and 2 and -4. I believe that's going to add up to, I'm just trying to do some mental math in my head. Well, all this and all this is +4 and -4 cancel, so I'm left with a half. So negative a +1/2, which is the answer. Okay. All right, there you have it. So just kind of, refreshing ourselves a little bit on the area underneath the curve and doing stuff like that. Tomorrow I'll go over all this stuff again, but really tomorrow I'm going to just do really one slide that we didn't get to, and that's this 2005 AP free response. Okay, so finished well under 30 minutes. That's good for y'all. I hope y'all enjoyed, and talk to y'all tomorrow.